Recorded rolling. Wednesday, January 28th. We're doing lesson 8 for natural logarithms. Right, so natural logarithms just have the base e. Right, so pretty similar. Yesterday we did base 10 logarithms. Now we're doing base e logarithms. Right, so just like yesterday, take notes about first half class. I'll do a bunch of examples from the book with you guys. Just turn those in. It should be easy points. You guys overall did pretty good with the notes yesterday. Easy points for the grade book. Right, and then the second half of class, you guys can work on this assignment, 8384 on Alex. That's a single assignment. And ask me any questions that you guys have. All right, so before I jump into natural logarithms, let's do a review of log rules in general. Last few days I've been showing this in class every day, right? But every day you see something, then your brain learns it a little bit better. So it's worth reviewing these again. Okay? So here's how to convert exponent into a logarithm or vice versa. If you have some base x, which is like right here, okay, to the power y z, I can take log of z, okay, and that's equal to y, okay, which was this power up here. Okay? All right, so that translation, okay, if you have a log of a times b, that could be the addition of two separate logs, log a plus log b. If you have log a over b, that's log a minus log b. If you have log a to the power b, you can take that power b, do it in front, and you have b times log a. If you have log base b to the a, where b is some weird base that's not base 10 and not base e, how do you put that in your calculator? Well, you can do a base conversion. So this was really handy yesterday. We used this a few times. It would be log a over log b, or natural log a over natural log b, as long as the bases match. Base 10, base 10, base e, base e. So that's the only two logs if your calculator knows. Then a couple of fun facts down here at the bottom. Log of some base, and then of that base to the power x is x. It simplifies to x. Right? Different ways to show that. Okay? Here's the natural log version of that same rule. Okay? Or if you switch it around, b to the power of log base b of x is also x. Right? And here's the natural log version of that. Okay? Right, so we got our log rules. Now, let's look at graph 2 before I jump into the book examples. Right? So here's your very basic y equals e to the x. Right? You guys have known this for a few weeks now. Okay? And then let's make a g of x here. Okay, and I'll call this ln and then x. So natural log of x. You guys see that those are definitely inverses of each other. Okay? Inverse means they flip over the line y equals that. That's one way to think of it. Right? Or if you switch what's x and what's y, then it creates the other equation. So that red and that blue line, those are inverses. Right? All right, so you guys see all that. And let's jump into the book here. Right, so I'm on page 81. Right, so in the longer video, which if you want to watch the longer video, second half class day, you can too. Right, we go over all these book examples at the beginning. Right, I did some graphs with you guys too there. Right, and also I did all the ones that I highlighted in green right here. Right, but with you guys right now in your notes, we're going to do the ones that I starred. Right, so let's start with number 5 right here. Number 5. Okay. Now what we're supposed to do is convert the exponential equation into a logarithm form. So number 5. Right, so do you guys write your name on your paper for your notes? So when you guys turn these in, everybody does have paper, right? So paper. Right, so when you turn these in, I'll give you credit. So number 5 says e to the power x is equal to 3. Okay, guys, go ahead. Guys, write that in log form. How can I write that as a logarithm?
Natural log is equal to
natural log of what is equal to what?
Natural log of 3.
3 is equal to
X.
X. Okay. Oh, you know what? I bet I could punch that in a calculator. Let's get a decimal approximation. I think that's all your book is looking for. Okay. But let's get a decimal approximation. So what is natural log of 3? It looks like approximately 1.0986 something. Okay. Now, if I take that decimal approximation and I plug it in right here, back to the original statement, shouldn't I get very, very, very close to 3? Let's see if it is. So I'll do second e to the power of, and then 1.0986. Yeah, sure.
I got 1.
You got what?
I'm doing natural log of 3, I got 1.
Here, I'll type it. Type natural log. And then 3. Yeah, ln. Natural log of 3. Should say 1.098 something. No, it's 1. Here, let's see what you're looking at. Okay. I don't know what that is. It might be fixed in the someplace. Let's do that. Okay. Natural log 3. Yeah, there you go. Okay. Yeah. All right. So all fixed. All right. So number 8. Right, so it's in the same section, so same text story. Okay. E to the x equal. Oh, actually, that's really similar. Yeah, that's right. Equals 8. Okay. Guys, how can you write that as a natural logarithm?
Log of 8.
Natural log of 8 is equal to x. Yes. Okay. So if Alex wanted an exact answer, you would type exactly that. If they ask for a decimal approximation, let's see what that is. It's approximately 2.0794 or something. All right. All right, guys, got that? Okay, number 14. 14 says write the log equation in exponential form. All right, so just the reverse of what we just did. All right, so this time they're giving you natural log of 4x is equal to 9.6. All right, guys, how could you write this in exponential form?
E to the power of 4x.
E to the what?
Power of 4x.
E to the 9.6.
Oh, yeah.
Sorry, my
Is equal to 4x? Like that? Okay. Actually, let's go ahead. I think that's all I'm looking for. Let's go ahead and solve for x anyway, though. Guys, to solve for x, what do you still have to do? One more step.
Divide.
Yeah, divide by 4. So e to the 9.6 divided by 4 could be x. Okay. Let's say that equals approximately, see what the calculator says. So e to the 9.6, and divide the whole thing by 4. Are you guys getting 3,691? Thereabouts. You guys getting that? Okay. You know what I want to do is push this to the side and let's play out some of those log rolls that you guys have been seeing every day. And let's solve this in a completely different way and see if it leads to the same answer. Okay. So back to the beginning. Natural log of 4x equals 9.6. What if I still want to solve for x, but I want to go about it a different way? Guys, what's the product rule here?
Log 4 plus 1.
Yeah. Okay.
Plus 2 on that.
Yeah, okay, yeah. That's what I was trying to articulate. Yeah. Natural log of 4 plus natural log of x is equivalent to the original statement. That's 9.6. Okay. Guys, you could say that, right? Could say that. Okay. And then could you subtract over natural log of 4? So natural log of x equals 9.6 minus natural log of 4. Okay. Okay. And then if you want to solve for x, how do you solve for x now?
Just like figure it out.
X equals, guys, what's this base right here? E? E to the 9.6 minus natural log 4. Right? Is this really this? Are we going to get the same number? That looks totally different. Let's find out.
No way.
Let's find out. So you guys type this with me. Let's do e to the power of, right, so we're doing some calculator practice also. Okay, 9.6 minus natural log 4. Okay. It's got to be the same number if all these log rules are correct. Yeah. It's the same thing. Right, 2 different ways to get in there. Same thing. All right, you guys good?
Yeah.
All right, number 17. Oh, and of course you could plug it to the original statement and check it. It would still work. 17. Actually, I want to do that real fast. Let's do it. So if right, I'm gonna type what's natural log of 4 times 3,691. Let's see if it's really close to 9.6. Yeah, it is. It is. Same thing. All right, so now we're ready for 17. We got natural log of 15 is equal to x. Okay. Let's solve that first. What is that? What is natural log 15? It's approximately 2.7081, something like that. Okay. But how could you write this in exponential form?
E equals
Huh?
E to the 15 equals x.
E to the x is 15? Okay. Sorry?
Natural log.
Right. Right. Yeah, so natural log of 15 is equal to x. Therefore, e to the power x is 15. Okay.
What's that form called?
So the top form is called logarithmic form, and this bottom form is called exponential
Okay.
form. Okay. Now I did get a decimal approximation for x, so let's plug that into this final answer and see if it gives us 15. Let's see. So e to the power of 2.7081. Yeah, it is. It's 15. All right, here. All right, 23. Write each expression, as a single logarithm. Yeah. I know there's some ALEKS questions that look kind of like this. So I got natural log of 125 minus 2 times natural log of 5. Okay, so this one just has numbers in it. Sometimes they have variables like x in them too, but I would do it. All right, so there might be a few different ways you could go about this that would be valid. One thing that catches my eye is this 5 versus this 125. Guys, can you write 125 as a power of 5s?
Yeah.
What is that? 5 to the power of what? Huh? 5 times itself, how many times brings you to 125?
3.
3. Yeah. Guys, isn't this really 5 to the 3? Right. Think of it like that. Right. This is just one way to think about it. Right. That might help us down the line. Right. Oh, what could I do with this 2 if I wanted to?
Automation that exponent.
Yeah, I could put this into this guy's exponent right here. Okay. So now I got natural log 5 to the 3 minus natural log of 5 squared, like that. Richard? Oh, and if I'm subtracting 2 logarithms, how can I consolidate that into a single logarithm? Natural log of what?
Oh, the natural log
Huh?
of 5, let's go, 5 cubed divided by natural log of 5 squared.
Sure. Yeah, so now we have a single natural log. 5 cubed over 5 squared. Okay. Remember that? Guys, that's this rule right here. If you have a difference of logs, that's a single log of a fraction. Or vice versa, depending on which way you're going. This and this. That's what we just did. Yeah.
I just moved D outside this D minus 2. Well, then that
Yeah, okay, that's another way to do it too. Okay. Because guys, if you have 5 times 5 times 5 on top, you have 5 times 5 on the bottom, what does this reduce to?
5.
Yeah, just 5. So the answer is just natural log of 5. Okay. That's the final answer. And yeah, there's different paths to the forest. There's different steps we could have done to get there. But regardless of exactly how you do it, you should get that. Okay. Let's get a decimal approximation and see. What is natural log of 5? It's approximately 1.609 something. Okay. Now, if I type in the original statement, which can't just there's no x's, right, then it should tell me that same decimal. Let's see what it is. So natural log 125 minus 2 times natural log of 5. Yeah, it's the same thing. Okay. So this and this is definitely the same thing. You guys good on 23? Yeah. All right, 26 down here near the bottom. 26. Okay. So we got 7 times natural log of 1/2 plus 5 times natural log of 2. Right. So same thing. Can you shove this into one single logarithm? Right. What are you guys thinking? What should I do first?
Make the exponents of 7 over 1/2 and 5 over 2.
Sure. Yeah, I can do that. Do it at some point. Take the 7 and make it the exponent on the 1/2, and take the 5 and make it the exponent on the 2. Yeah, I can do that. So it'll be like natural log of then 1/2 to the power of 7 plus natural log of 2 to the 5. Sure. What do you guys think next?
Multiply? Like natural log of
Tell you what, I'm really itching to do. Remember last time I was saying 5 goes into 125 some power. Right? Does this 1/2 and this 2 have anything to do with each other? 2 to the power of what is a half? -1. Okay, let me go ahead and take care of that. Okay. So isn't this really natural log of 2 to the -7 plus natural log of 2 to the 5? So, okay, same thing. Okay. What do you guys think next?
Then just minus.
Okay, so guys, the rule is if you're adding 2 logarithms together, what can you do with their inside pieces? Multiply, multiply. Okay, so this is really, all right, now we're down to 1 logarithm. It's 2 to the -7 times 2 to the 5. Sure?
Yeah.
Okay, now this right here, okay, I think we got a few more steps. This could combine, make natural log of what? 2 to the -2. Okay. That might be a perfectly valid answer right there because that's consolidated to 1 logarithm. Okay. Now, if it were me, I would do one more step. Guess what's one more step you can do?
Flip their -2, so it's 1/2 positive.
Oh yeah, okay. Actually, that's 2 different ways you could finish this off. So what I would have done is -2 times the natural log of 2. Okay. But yeah, some of you guys are saying, well, actually, you could say this is equal to natural log of 1/4. That's the same thing. Okay. I bet these are the same thing. You guys think they are?
Yeah.
Let's see. Let's try and calculate. -2 natural log 2. This is approximately -1.3863. Natural log of a quarter is approximately -1.3863. It's the same thing. So this is a nice answer. This was also a nice answer. So I think either one of those is perfectly fine. You guys good?
Yeah.
Okay, 26. All right. Let's do 3 more. So I have 1 more basic example, and then a couple of word puzzles I'm going to do with you guys. Okay. Now there are a bunch of other word puzzles too that I highlighted in green, so I did those already on the longer video if you like. Okay, so number 38 says solve this equation round to the nearest 10,000. So we have natural log of 5x plus natural log of x is all equal to 7. Okay, well, we got to solve for x. So what do you guys think is a good first step?
Make it 5x squared.
Yeah, exactly. This is one giant logarithm, natural log of 5x times x, which is called 5x squared. Yeah, right, and that's equal to 7. Is that okay? Great, because all I did, what you guys were telling me to do is this rule right here. Add 2 logs, you can just multiply their inside parts. What next?
Put the do natural log 5x.
Okay, but since what we're trying to solve for, well, guys, our end goal is to get x equals something. So it's going to be a few steps, and then we'll have x equals something as the last step.
Natural log 5 with natural log or plus.
Yeah, okay, you could write this a bunch of different ways, but to help you unbury something from inside a logarithm, what's the opposite process of a logarithm? Exponents. Yeah, exponents. We gotta make an exponential. Okay. So how can I write this in exponential form?
E to the 7 equals 5x.
Exactly. E to the 7 is 5x squared. And now we're closer to being able to solve for x. Okay, so now can you guys finish this off with just regular algebra? Divide both sides by 5. So x squared is e to the 7 divided by 5. Okay. So x should be the square root of that. Now, okay, and it does want a decimal approximation. Okay, you guys, before I get a decimal approximation, when you take the square root yourself, like x squared equals something, and so you take the square root yourself, do I normally put a plus or minus on here? A plus or minus? Yeah, okay. But, guys, plus or minus, so that looks like 2 solutions. Problem is, only one of these actually works, and the other is extraneous. Guys, which solution does not work at all? Negative. Okay. And the answer is really apparent on a log graph. You guys remember this blue line, this blue curve? That's natural log x. Guys, does this blue curve have any negative x values? No. There's only positive x values. Right? So there's a domain restriction. So if you look back at the original statement, I'm taking natural log of 5x, natural log of x. Yeah, I cannot include the negative one. So it has to be only the positive one. Positive only. Right, so let's get decimal approximation here. What's the square root of e? Oops. Square root of e to the 7 over 5. I'm looking at 14.8097 about. There you go. Decimal approximation. All right, guys good? All right, number 47. Population. The growth rate of a population can be represented by A equals A naught times e to the RT. Ooh, it looks like continuous compounding. Also kind of reminds me of exponential decay, or like radiocarbon dating. But this is population. So A naught's the original population. R is the annual growth rate. The world's population in 2008 was this number. Here's the growth rate. When will the population reach 9 billion? Okay. So we're going to call this A naught right here 6.6 billion. So 6,641,000,000. All right, and then they just rounded off right there. Okay, so there's that. Okay. We're going to target. We're going to say, hey, when's the world population going to reach 9 billion? So here's 9,000 million billion. And we know the growth rate is 1.2%. Guys, how do you write 1.2% as a decimal? As a decimal?
0.012.
0.012. Right? 0.012. Okay. And we got to solve for this time right here. Right. Right, guys see that? Okay, so what do you think is the first step? First step. Okay, divide this 9 billion by this 6 billion. So let's go 9 billion divided by 6,641 zip 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 zip. All that. That's equal to e to the 0.012t. Guys, what's the next step? How do you get t out of the exponent? You have to apply a. Huh?
And that's supposed to be 9 billion.
Yeah, it was 9 billion.
Okay.
But all these zeros cancel out all the way up to like the millions. Because 9 billion over 6 billion. Can I play a logarithm? Let's do a natural logarithm because there's an e right here. So if I take the natural log of this over this, that's the same thing as 0.012t, right? And what's the last step? How do you solve for t? Divide this r down. So the amount of time to reach the population of 9 billion would be 1 over 0.012 times natural log of this ratio. Let's get a value on that. So 1 over 0.012 natural log. Looks like about 25.3 years after the initial year. So I guess after 2008, this was a year. Okay, so the base year is like 2008. Okay. So 25 years later. Yeah. Hey, you guys got that? Okay. Let's do one more. Okay, 48, finance. Janie's bank pays 2.8% annual interest compounded continuously in her savings account. She invests 2,000 in her account. Use A equals PE to the RT to say how long it's going to take her initial deposit to double in value. Ooh. Assume she makes no more deposits or withdrawals. All right. So 48. So we got A equals P e to the RT. Okay. She's going to put in $2,000, and for that to double, it would go to $4,000. Okay. Well, it turns out that any amount of money she wants to double takes the same time, so it doesn't matter how much she put in, really. Okay. But you guys got to see that. Okay. The interest rate is 0.028 as a decimal, and that's compounding continuously, hence we're using this formula, and we're solving for how much time does that take. Okay. So first step, divide over 2,000, and that gives me 2. That's e to the 0.028t. Make sure you guys are following. Guys, where did I get this 2 from?
Divide
4,000.
divided by 4,000 minus 2,000.
Exactly. It's 4,000 over 2,000. All right. What's the next step?
For R, 0.028.
Yeah, 0.028. Because, yeah, natural log is the next step. Okay. So R is 2.8% is what they told us. Okay. But as a decimal, it turns into, yeah, natural log. So natural log of the left side is equal to natural log of the right side, which just ends up being this exponent. And last step is divide down this coefficient. So the amount of time it takes her money to double is whatever this is. Okay, years. Right. Now it says round your answer to the nearest quarter of a year. Nearest quarter. So let's do that. Nearest quarter. So natural log of 2 divided by 0.028. Okay. So that's approximately 24.755 to something here. So the nearest quarter would be 24.75 years.
Actually,
Okay.
45 because
Well, they said the nearest quarter.
we have to round.
Okay. It says to the nearest quarter. So the only possible answers are 0, 25, 50, 75, 100.
Oh, that's
Okay.
right.
Near the quarter. All right. All right. So you guys got rest of class to work on Alex, watch video, or ask me questions.